Up next, we are going to, this is a very large word problem that we are going to work on. So first things first, let's go ahead and read the problem and break it apart little by little. So it says, a tree harvester is often interested in the volume of a tree's trunk because most of the wood volume is located in the trunk. If you think about it, the branches don't have much wood, the trunk has the majority of it. So a tree harvester estimates the trunk of a sequoia tree to have a height of about 50 meters. I'm just going to label things as we come in. So height is 50 meters, and a base diameter of about 0.8 of a meter. If you guys just logically think about just a tree trunk, it looks like something like this, right? It's rounded, and it's got a circular top on the bottom. So we're looking at a cylinder, by the way. Okay, so part A says the wood of the sequoia tree has a density of about 450 kilograms per cubic meter. So I'm going to go ahead and label that. I guess I should call this diameter, and then density is 450 kg per meters cubed. Then we need to find the mass of the trunk rounded to the nearest kilogram. So we need to find the volume of the tree trunk. We're assuming it's a cylinder. So first off, what we need to do is we need to use our knowledge to find the volume. Then we can use the density equals mass over volume to find the mass of the trunk. I'm going to work down here on the bottom. So the volume of a cylinder is pi r squared times h. When you fill in the pieces, you'll get pi times 0.4 squared, which is 0.16, times 50, which gives you approximately, which is, rounded to the nearest hundredth of 25.13 meters cubed. Now, that is the volume. We know the density, so if we look at the density equals mass over volume, we can go ahead, put those pieces in, cross multiply, and solve for the mass. So density is 450 kilograms per meters cubed, and that is equivalent over mass over 25.13 meters cubed. When we multiply both sides by 25.13 meters cubed, cancels on that one side, and then I guess I'll just make a little more room on the other side. Then the meters cubed cancel, and you are left solely with kilograms. So times this by 25.13 meters cubed. You see the meters cubes cancel. And then you have 450 times 25.13, 11,309 kilograms is our mass. So the mass of the trunk is approximately 11,309 kilograms. Okay, so we're just doing basic cross multiplying, making sure we're in chemistry, they call it dimensional analysis. We are changing our units and we're doing them properly. So next up, it says each year the tree trunk forms new cells that arranges themselves in circles called growth rings. These rings indicate how much wood the tree produces annually. Says the harvester estimates that the trunk will put on a growth ring about 1 centimeter thick, and its height will increase about 0.25 meters each year. How many cubic meters of wood does the tree trunk produce after 1 year? And then if the tree trunk grows at a constant rate for the next 5 years, will it produce the same amount of wood each year? So let's go ahead. We need to make a table. We're going to talk about height. We're going to talk about radius, and then we're going to talk about volume on part B. Okay, table time. So in there, certain things we need to cover. We need to cover the year. We need to cover the height because we see the height's going to grow. We need to have the radius. They call it the base radius. And then we need the volume. Thankfully, these are all extremely connected and they follow that pattern. So we'll be able to use the work for it. So we've got year 1. In year 1, the height has increased 0.25 of a meter. So if we started with 50, we're at 50.25. Our radius grew at a rate of 1 centimeter. So if we are looking at meters in our normal piece, we need to change that back. So if we're going 1 centimeter, setting up the conversion if you weren't aware, 1 centimeter is can be changed over by saying, well, 1 meter is 100 centimeters. That crosses out and you get 0.01. 0.01. So that turns it into raising it up a point. It's growing 0.01 each year. Now, we were given the diameter, which means the radius at the original is 0.4, so we're going to be at 0.41. The volume, so we need to look at pi r squared times the height. When you plug that in, you do pi times 0.41 squared times 50.25. You will get 26.54. Now, I think it's slightly easier if we just go ahead and follow the pattern. So year 2, 3, 4, and 5. Let me erase a little bit of this work, just so I can finish that table out. Okay, so going up in years, 1, 2, 3, 4, 5, our height is going up 0.25 meters each time. So this is 50.5, 50.75, 51, and then 51.25. Our radius goes up 0.01 each time, so now we're at 0.42, 0.43, 0.44, and 0.45. Last up is the volume, so that will take a little bit more work, but it's pi r squared times h. Plug those in, you will get 27.99, 29.48, 31.02, and 32.60. So now that we have seen the volume as each year goes on, we need to see what it's growing by to see if it's growing at a constant rate. How do we find that? Well, you can take that second term and subtract it by the first term to see that piece. So 27.99 minus 26.4 says that you are going to be adding 1.45 between years 1 and 2. So 1.45 cubic meters. Going from years 2 to 3, you're adding 1.49. Years 3 to 4, you're adding 1.54. And then years 4 to 5, you're adding 1.58. So those are not constant. That was the whole point of the question. It grows at a constant rate. However, it will not produce the same amount of wood. It will be increasing, and it won't, it'll continue to grow, and the wood you get will continue to grow as well. So that's what this problem is asking for. This one was a longer one, but hopefully that made sense. If not, go back through, make sure you get and understand the volume, the radius, how we get from the years, how we got the mass and the density. So make sure you check that before you move on.